Today we're going to be talking about how to sketch polar curves. And in this particular video, we're going to be talking about two different polar equations. The first one, which we'll call equation number 1, is r equals 7 times sine of 2 theta. And the second one is r equals 6 plus 4 sine theta. And the method that I use for sketching polar curves is really common, but it works really well. The first thing that we're going to do whenever we're asked to sketch a polar curve is we're going to take whatever's inside our trigonometric identity and we're going to set that equal to pi over 2. So in the case of equation number 1, we're going to set 2 theta equal to pi over 2. And then we're going to solve for theta and we'll get theta equals pi over 4 when we divide both sides by 2. For equation number 2, we'll take, again, whatever's inside the trigonometric identity, in this case theta, and we'll set that equal to pi over 2. Of course, we've already solved for theta, so we don't have a second step. The reason we do that is because we're going to be marking off our x-axis when we plot these on a Cartesian coordinate system. We're going to be marking off our x-axis in increments of whatever we got here for theta. So in the case of equation number 1, we're going to be marking off the x-axis in increments of pi over 4. So we'll get pi over 4 here, then we'll get pi over 2, we'll get 3 pi over 4, and then we'll get pi. And then we would get 5 pi over 4, right? And we could keep going. We mark off the x-axis in increments of pi over 4. For equation number 2, we're going to mark off the x-axis in increments of pi over 2. So we'll have pi over 2, then we'll have pi, then 3 pi over 2, and then 2 pi. Right, and we could keep going. We would get 5 pi over 2, etc. So we're just going to mark off the x-axis in those increments. That's the only reason we do it. And it ends up being convenient for us because when we try to evaluate each of our polar equations at the points that we've marked off here on the x-axis, we're going to be able to plug those in and use the unit circle, which I've drawn a basic unit circle out here, but all the points we're going to plug in are the 4 points here on our unit circle that I've identified. The point here, 1, 0, 0, 1, negative 1, 0, and 0, negative 1. And those points are obviously really easy to evaluate as opposed to something out here that's like an angle pi over 4 and the coordinate is square root of 3 over 2 or something like that. So sticking to these 4 corners here on the unit circle makes things a lot easier, which is why we do it this way. So now that we've marked off our x-axis in increments of theta that we solved for down here, we're going to go ahead and plug each of those points into our polar equation and just start plotting on the Cartesian coordinate system or the xy coordinate graph. We're going to plot them here on the xy coordinate plane and then we're going to translate that to the polar coordinate system. So let's go ahead here and take equation number 1. So we've got r equals 7 sine of 2 theta. And now we're going to go ahead and figure out the value of the graph at each of the points we've marked off here on the x-axis. So we're going to start with 0, we're going to start with the point here 0, and then we're going to find pi over 4, pi over 2, etc. So when we plug in 0 for theta, right, we'll be plugging in we'll be plugging in for theta and solving for r. So when we plug in 0, we'll get 7 sine of 2 times 0, which will give us 7 sine of 0. Well, sine of 0, remember when we go back to our unit circle, all of our coordinates on the unit circle, you can consider the x-coordinate as cosine and the y-coordinate as sine. So when we say sine of 0, we know that we're taking the y-coordinate, sine, of the angle 0, which we know to be here. So we want this y-coordinate right here, which is 0. So we get 7 times 0, which of course is just equal to 0. So that tells us that our point here is at 0. Now let's go ahead and look at pi over 4, our next increment, right? We'll get r equals 7 sine of 2 times pi over 4. Well, we know that 2 times pi over 4 is pi over 2. And now that takes us to this point here on the unit circle. Pi over 2, we're looking at sine again, so we want the y-coordinate there, which we know is 1. So we get 7 times 1, which of course is just equal to 7. So then here at pi over 4, let's go ahead and call this 7 here. At pi over 4, we're going to get the point 7. If we went ahead and plugged in pi over 2, let's just give ourselves some more space. If we plugged in pi over 2, we'd get, r equals 7 sine of 2 times pi over 2. Our 2's will cancel and we'll be left with 7 sine of pi. Well, sine of pi, here we are at the angle pi, and we know sine to be the y-coordinate, so that's the y-coordinate there, which is 0. 7 times 0 gives us 0. So again, coming back over to our graph here, our y value is then 0. Let's go ahead and plot just one more point to see what this is going to look like. If we plot 3 pi over 4, we'll get 7 sine of 2 times 3 pi over 4, which is going to be 7 times sine. We'll get 3 pi over 2. And 3 pi over 2, here's our angle, 3 pi over 2. Our sine coordinate there, or our y coordinate there, is -1. So we'll get 7 times -1, which is -7. So we can see here then that our graph is going to be down here at -7. So what this tells us, if we kept going, is that our graph would look something like this. It would come up this way, it would come down in this parabola-like shape, it would come down here to meet -7, it would come back up here to meet pi, and then here at 5 pi over 4, we'd be back up here at +7, and that would just repeat itself. It would come up and down and up and down and repeat itself in that way. So now that we have the graph of the function on an xy coordinate plane, we want to go ahead and translate this to the polar plane. And let's actually do ourselves a favor here and mark off these different sections in different colors. So this here will be orange, this first section. The second section here will be green, and we'll use this color coding to help us translate. We'll get this awkward teal color here, and then blue, and then purple. So hopefully this will help us make a translation here. So now we want to take each of these points and plot them on a polar coordinate system as well, and it makes it kind of easy now that we've plotted it on an xy coordinate system. So what we're going to do is we're going to start with this point here. Well, that's at the origin, 0, 0. So when that point is at the origin, the polar coordinate system is the same thing. We have this point here at 0, 0, the origin, so that's our starting point. Then, as we move between 0 here and pi over 4, we're going to move up here to 7. So if you think about it on a polar coordinate system, pi over 4 and all of these increments here on the x-axis are angles in the polar coordinate system. So the angle pi over 4 is right here, right? This is the angle 0, and as I move up toward this direction, this right here is the angle pi over 4. So as I move toward pi over 4 from 0, I come out a distance of 7. So what I end up doing here is I wrap around up here, and as I approach pi over 4, I come out a distance of 7 from the origin, right? So we can call this line here 7. This is a distance of 7 from the origin. So that's how we plot that, and that's going to be the orange section of our graph. So we'll go ahead and draw that. Then you notice the second section here, as we come, let me grab a different color, as we come back from pi over 4 down to pi over 2, well, the angle pi over 2 on our polar system here is here, pi over 2, and we can actually mark this off here. This will be pi, this will be 3 pi over 2, just like the unit circle. This comes back to 2 pi, and then, this line here would be pi over 4. This would be 3 pi over 4. So these are our angles, right? This will help us a little bit. So now this green section of the graph, right? We're here at this point here, and as we come back toward the angle pi over 2, so as we move from here to here toward pi over 2, notice that our xy coordinate system graph comes back toward 0, right? We head back toward the x-axis or 0, which means that our polar graph is going to curve back in here toward the origin 0, right? So we curve back toward 0. Now notice that we are at this point crossing the x-axis, right? We were above the x-axis for this whole range here, and now at this point here at pi over 2, we're going to dip below the x-axis. Well, what that means is that we're going to cross the graph, right? We started here at this point. We're going to cross over the graph, and as we move from the angle pi over 2 to the angle 3 pi over 4, we know this here is the angle 3 pi over 4. On the angle 3 pi over 4, we're going to be at -7. So if we were at +7, we would be out in this direction, +7. But because we're here at -7, right here, we need to move out this way, the opposite way, a distance of 7. So this section of the graph will be this teal color. As we move toward 3 pi over 4, we're going to be out -7, which will be something like this, right? And we'll end up at this point here. Then for the blue section of the graph, as we come back here, we come from -7 back to 0 as we approach the angle pi. Well, here's the angle pi. We're coming in this direction. So we come back toward 0 here, and we wrap back in, we get to the origin. If we kept going with purple, right, here at 5 pi over 4, the angle 5 pi over 4 is right here. And notice that we are at +7 here, which means we're moving in this direction. So that means that our point here is going to be in this direction of the angle 5 pi over 4, and we come out here. Our graph would continue like this. And if we kept going, we'd wrap back in toward the origin like this, back out here, and then back in, and we would realize that we have a four-leafed graph here on the polar graph. So contrast that with the equation r equals 6 plus 4 sine theta. If we plug in each of these points, right, we start with 0, and we plug that in to our equation, and we'll move through this one a little bit more quickly. But if we plug in 0, we'd get r equals 6 plus 4 sine of 0. We know that sine of 0, right, we're here at the angle 0 on our unit circle. The y-coordinate there is 0. So this whole thing's going to be 0. We're just going to be left with 6. So that means we're out, we'll call this here 6. So we start here at 6. Then when we plug in pi over 2, we get r equals 6 plus 4 sine of pi over 2. We know that sine of pi over 2 is 1. So we get 6 plus 4 times 1. That's going to give us 10. So we're out here at 10. We'll call this here 10. We're out here at 10. Then if we plug in pi, we'll get r equals 6 plus 4 sine of pi. We know that sine of pi is this number right here, 0. So again, that'll go away and we'll come back to 6. If we plug in 3 pi over 2, we'll get r equals 6 plus 4 sine of 3 pi over 2. We know that sine of 3 pi over 2 is this -1 number here, so we'll get r equals 6 plus 4 times -1. That's going to give us 6 minus 4, which is equal to 2. So we come down here, we'll call this 2. We come down here to 2. And if we kept going, this is what we'd get. We'd come up here to 6, from 6 to 10 like this, then down from 10 back to 6, 6 down to 2, then here at 2 pi, we're back up to 6, and then here at 2 pi, we come back up to 10 as we approach the angle 5 pi over 2. And we could keep going like that, so we'll go ahead and mark these points. So we keep going. Well, same thing when we translate this onto the polar curve here. At the angle 0, right, this here is the angle 0, we are out a distance of 6. So here's the angle 0, we move out a distance of 6. We'll call this right here 6. So this will be first here, our orange point. So we come out a distance of 6. Then, as we move toward the angle pi over 2, right, we move toward the angle pi over 2, and let's just go ahead and mark this off. we've got pi over 2 here, pi, 3 pi over 2, and back to 2 pi here. So as we move here from the angle 0 to the angle pi over 2, our graph goes from 6 to 10. So here on the axis we're at 6. When we come out here, we're going to be at 10. So we come all the way up to 10, call this 10, 6, and that'll get us here to 10. Then as we move from pi over 2 to pi, here pi over 2 to pi, we come down from 10 back to 6. So if we plot a point here, again we'll call it 6, we'll be there at that distance, and we'll connect these in a second. Then as we move from pi to 3 pi over 2, or pi to 3 pi over 2, we move from 6 down to positive 2. So we'll call this here positive 2 in that direction. This is 2. And if we connect these, right, we'll get orange here, which comes up to 10. Then we get green that comes from 10 down to 6. We get teal that comes from 6 to 2, and this is what it's going to end up looking like. And then from 2 here we'd come back to 6. And then we would repeat. Purple would wrap around again with orange, and we could keep going. And it will just be this continuous loop around the graph over and over again. So what's interesting, and one of the conclusions I want to draw from comparing these two graphs is, you notice that this equation, when we graph it on an xy coordinate plane, it's above the x-axis, then it's below the x-axis, then it's above the x-axis again. And what we realize is that that graph gives us this pedaled graph on the polar coordinate system where we cross over the graph, right? We get this pedaled approach and the graph crosses itself. Contrast that with this graph over here, 6 plus 4 sine theta, which is always above the x-axis, right? This whole graph is above the x-axis, which means that when we translate this into a polar system, the graph is never going to cross itself. It's going to just come in this loop here, but we're never going to end up with this pedaled approach, right, which we get when we cross above and below the x-axis. So just kind of interesting to look at how these things graph out differently given what they look like in an xy coordinate plane. So that's it. I hope this video helped you guys, and I will see you in the next one.